This is part 1 of Tangents and Velocities. Since this is the first of many videos on calculus, let's talk about what on earth calculus is. So it's a branch of mathematics dealing with continuous change and motion. Rather than looking at a specific moment or point in time, we're looking at quantities that are changing, often with respect to quantities that are also changing, and looking at how they're changing. Calculus has many applications and is typically split up into 3 parts. If we look at some Calc 1 topics, so limits, differentiation, and integration, which then can be applied to more calculus, which has to do with related rates, linear approximation, and optimization, these concepts and skills can be applied to biology, economics, engineering, medicine, physics, statistics, and even more. Because all of these fields have quantities that are changing, so calculus will help us out. Calculus has 2 main branches, the first of which is differential calculus. Differential calculus has to do with finding the tangent to a function at a point. So we might be interested in the tangent at this point on our function, the tangent at this point on our function, or the tangent anywhere on this function. And we're interested in finding the slope of that tangent line for any of the infinitely many points on a function. Doing this for graphs, doing this for equations, and all the different ways we can represent a function. The other main branch of calculus is integral calculus, which is concerned with finding the area underneath a curve and interpreting what it means to find the area underneath a curve. Again, we're looking at this not only for graphs, but finding the area under a curve if all we have is an equation, or again, any other representation of a function. So let's do some quick review of a couple different concepts that we'll need. A secant line is a line between 2 points on a curve. So if we have this point and this point, the line between these 2 points is a secant line. The average rate of change of a function on an interval is the slope of the secant line. So if you need to find an average rate of change on an interval, you can find the slope between these 2 points. The tangent line is the line at a point. So if we're interested in this point, the tangent line is the line that touches this point, but doesn't intersect with any of the points on the function that are nearby. It's important because the instantaneous rate of change, so the rate of change at one particular instant for a function, is the slope of the tangent line. So if we need to find the instantaneous rate of change for a function, then we need to find the slope of a tangent line, which is one of the main problems that we focus on in Calculus 1. A normal line is the line that is perpendicular to the tangent line at the point of tangency. So that means that we have to go through the point of tangency and be perpendicular to the tangent line. So that means that my normal line and my tangent line form a 90-degree angle. So this purple line is the normal line at that point. Let's say that we want to find the instantaneous rate of change at this point here. Well, that would mean that we want to find the slope of the tangent line through that point. So let's say that the input at this point, which is usually an x value, is a, and that the output at this point, well, that would be f of a. So we have this point of tangency, which is the point a, f of a. And that tangent line would look, well, not quite like that, would look something like this. So we can see that there's a tangent line. We're just not quite sure what the slope of that tangent line is. So let's think about slope. slope is equal to the change in y, where I'm using that Greek symbol delta, which looks like a triangle for change, over the change in x. So that's the difference between our y values, y2 minus y1, divided by the difference between our x values, so x2 minus x1. And we're interested in the slope at that point of tangency. So at the point x is equal to a. And that will be equal to, well, we only have this one point, so let's just use that point. So that would be the difference in our y values, so f of a minus f of a, divided by the difference between our x values, so that's a minus a, which gives us 0 over 0. Unfortunately, 0 over 0 really doesn't give us much information. And if we had tried to find the slope of the tangent line at any of these points using this method, we'd get 0 over 0. But the slope of the tangent line through each of these points is not the same. So 0 over 0 just doesn't give us any information at all. So we need another way to find this slope. And the first part of Calc 1 is very interested in the many ways we can try to approximate and then eventually actually calculate the slope of a tangent line. But for now, it just seems one point isn't going to give us enough information. So instead, we'll look at 2 points. We'll look at some other point on the curve, which makes it so that we can create a secant line between this point and the point of tangency. And then we can look at the slope of that secant line. And as this other point gets closer and closer to this point of tangency, we'll notice that the slope of the secant line changes a little bit. And as we get closer and closer and closer, the slope of the secant line gets closer and closer to the slope of the tangent line. So the first thing we'll do in calculus is approximate the slope of a tangent line by taking successive slopes of secant lines and trying to see if they get closer and closer to a particular value, which we hope will be the slope of the tangent line.